Hello Math 152 students. In this video, we'll take a look at 11.2 and some examples with matched pairs. So in a minute, we're going to look at our 5 steps for matched pairs, but we want to understand our conditions first. So we will say to test hypotheses regarding the mean difference of data obtained from a dependent sample, use the following steps, which we'll see on the next slides, provided that we have some conditions check. So these 4 bullet points give us those conditions. The first condition is the sample is obtained using simple random sampling. You want to make sure that you're not using a convenient sample and that you don't have bad data to start with. So we'll look for some indication in our problem of random sampling. We do want the sample data to be matched pairs. We need to have an explicit pairing or a way to pair the data in the problem setup. Then the third condition has to do with our sample size. We either have to have the differences are normally distributed with no outliers, meaning we could check our QQ plot and our box plot, or the sample size is large. So another way to say this is for large data sets greater than or equal to 30, you don't have to worry about QQ plot and box plot, just like the chapter 10 case. But for less than 30 data points, you have to make sure the QQ plot checks out and the box plot checks out. The big difference is here, we're doing the QQ plot and the box plot on the differences for paired data. Then the last thing is that the sampled values are independent. Now I just want to contrast this with the matched pairs idea, because the matched pairs talk about sample 1 and sample 2 being matched up so that we have a pair. But then this fourth bullet point is talking about the values within our data set. In other words, the first pair of data and the second pair of data aren't intertwined. They're independent from each other. So if these conditions check out, we are ready to proceed and set up our hypothesis test. The setup is the exact same 5 steps we've seen before. We'll first of all determine our null and alternative using either two-tailed, left-tailed, or right-tailed. The big difference here is we are going to take a look at the differences. So you'll see this mu sub d, which is talking about the d is for differences. And we'll try to understand in a minute where this difference of 0 comes from. It'll make more sense when we see a specific data set. But you'll either have the difference equals 0. Another way to say that is there's no difference between the two. Or the difference is not 0, there's some difference. If you're left-tailed, your difference is 0 or less than 0. Right-tailed, equal to 0 or greater than. So again here, it'll make better sense with the concept of a 0 difference when we see some data. Then make sure we've specified our level of alpha. Go to StatCrunch, get your test statistic and your p-value. Step 4, if your p-value is less than alpha, you reject your null and accept your alternative, and state the conclusion in everyday language. So one thing to note is that these procedures are robust, which means that minor departures from normality will not adversely affect the results. However, if your data has outliers, you should be careful and really stop. So what does this mean for us? It means that we want our QQ plot, which addresses the normality, to look pretty close to linear. We also want to check the box plot, which will tell us if we have outliers. If we have some issues with our QQ plot, we're looking for it to be roughly linear, that's okay. If we have outliers, that's going to be a hard stop for us, or an issue where we're going to say maybe we shouldn't use this procedure. Okay, so let's take a look. We're going to look back at our hotel example. It's a slightly different scenario with a different setup. We're looking at 10 pieces of data rather than the 8 in our previous example. They tell us the following data represent the cost of a one-night stay in Hampton Inn Hotels and La Quinta Inn Hotels for a random sample of 10 cities. Test the claim that Hampton Inn Hotels are priced differently than La Quinta Hotels at the alpha equals 0.05 level of significance. So notice we already addressed why this is paired in our 11.1 video, but notice For the 10 cities, we chose one from Hampton Inn, one from La Quinta, from the same geographic area. So we have a natural pairing. Let's take a look at what our data actually looks like. They were nice enough to tell us the 10 cities where the data came from. And it doesn't make a lot of sense, for example, to compare Orlando to maybe Seattle. Notice both Seattle numbers are larger than the Orlando numbers, but it's interesting that we have kind of a similar price gap. So, what can we say? If we were interested in knowing if there's a price difference, we're asking if this data set has a mean difference that's different from this one, but we want to preserve the pairing by the geographic locations. So one way to do this is to go into StatCrunch and ask it to do the differences, to say, how much higher is Hampton Inn than La Quinta in each particular city? So let's switch over to StatCrunch, and I want to show you how to do that. Notice I went ahead and typed my data in and labeled those. One thing you can do just with your calculator is to manually do the difference. 129 minus 105, put it in your third column. 149 minus 96, put it in your third column. Another way to do it, though, is to use StatCrunch's pre-done calculators. It's kind of like Excel, but you can't just type your formulas quite like you can do in Excel. Okay, so if we go in and go to your data and compute expression, you can hit, notice I've already been messing around with this a little bit, so it has something that I've already done, but I want to show you how to build. Yours probably will not have that. You can build expressions based on your column. So notice you have all these different functions like absolute value, cosine, different really math functions that we haven't gotten into in our course, but you also have the columns. So you can choose your Hampton, double click it, and you can say, I want to find the difference between the two, and ask it to compute this expression, and hit OK. Okay, so it puts your expression, and it's going to compute it and add it to your third column. Okay, so it tells us new column added, thank you, and we have all of those price differentials. Notice most of the price differentials are positive when we do Hampton minus La Quinta. In one case, the La Quinta was more expensive, but in all the others it was not. And in fact, the largest differential was in row 3. There's a $100 price difference. Let's just take a look back at our data. Looks like that was St. Louis, right? But none of the others were $100. They were closer, looks like, for most of these, in the neighborhood of 40 to 70. Some variation there. So looking at these numbers, we want to know, do these differences indicate a price difference? If there's no difference between the two, we would expect these values to be 0. So that's why we're seeing that difference equals 0 in the null hypothesis, or difference not equal to 0, greater than 0, or less than 0. So let's go back to our slides. We already established this is a matched pairs design, and we want to first compute the differences. So we asked StatCrunch to do that. Here we have it just laid out here. Notice you can compute the average and standard deviation of that third column using StatCrunch. Most of the time you really don't need to do that first. The other thing we need to do is verify our QQ-plot and our box plot for our differences. So notice this part says verify that the differences come from a population that is approximately normally distributed with no outliers, because the sample size is small. We only have 10 pairs of data, and we would need 30 to avoid checking. So what we need to check is our QQ-plot and then our box plot. If we look at our QQ-plot, make sure we're creating a QQ-plot of your differences. This looks approximately linear. I might have some concern about this point. One of the things about our procedure is that we said small departures from normality aren't a big deal. If we were worried about this too much, we could look at our critical values for our QQ plots. In this case, I want to go ahead and show us what the box plot looks like, because sometimes if you have a problem with one, you'll also see some problems with the other. So in other words, this is approximately linear, maybe some slight concern here. Follow it up, look at your box plot. And we're looking at the differences. I want to make sure I use my fences to draw outliers. And we'll look at the horizontal orientation. So notice what I see here, an outlier. This is a problem. And if we look back at our data set, that -10 was much lower than any of the other values. It was the only place where the La Quinta was higher than the Hampton. So it turns out that this is a problem, and if we go back, this is actually kind of the only point I was a little concerned about on our QQ plot. So what does this tell me? This tells me that I have an issue. Anytime you have an outlier with a small data set identified on your box plot, you really don't want to proceed. So why did I show you this example? Because sometimes when we're doing book example after book example, it looks like everything checks, and it doesn't always. If I wanted to still test this hypothesis, I would need more than my 10 data points. I would have to gather at least 30, because if I see some outliers with a less than 10, my conditions aren't going to check. I would have to gather some more data, make sure I have more than 30 data points, and then I could proceed even if you had outliers. So it's not that outliers always stop the process. It's that with a small data set, outliers are going to stop your process. So we'll take a look at another example. We'll cut this video off so we don't run out of time, where we check these conditions again and we see something where we can proceed.